All right, let's finish up the antiderivatives and indefinite integration notes. So, suppose that f of x and g of x are antiderivatives. Again, without me even saying that, we know they're antiderivatives because we're using capital F and capital G. F of x and g of x are the original functions, and like I said, capitals are used to represent antiderivatives. C as a constant, I'm also using K as a constant in here as well. So, just like we had with limits and just like we had with derivatives, and I talked about this in the last example from the 651 notes, basically we can split these up. Well, that's in the next part. First part, sorry, I'm getting ahead of myself, but still the same thing with limits and derivatives. Whenever we have a constant, we can always just factor that out of the integral. So you can see that here all we did was factor the constant out there. And then we would take the integral of your f of x, okay, we take the integral of f of x dx, and that's where you would get your capital F of x dx, and the constant would be outside. Now you might be saying, well, shouldn't this be distributed through? If I take a constant k times a constant c, what do I get? Another constant c. So we don't really have to like say that differently. Later on in the year when we get into differential equations, we will talk about different constants and how we represent them separately, but for now you just take and multiply the constant by the antiderivative of function f of x, and then plus a constant outside there. Now, the other part that I started to say, if we are adding or subtracting, just like we did in the notes from yesterday, two functions, or 3 or 4 or 5 different functions, it's the same thing as taking the integral of those functions separately. Now, when we take the integral of this one, we will get capital F of x plus c, and then this one over here we'll add or subtract capital G of x plus c. But when we, again, going on the same thing as up here in this example, if we add a constant and a constant, we're not going to write that as 2c, because what is 2 times a constant? And that is just another constant. So what we're doing is we're just kind of lumping them together into one single constant there. So, and that's just the notation that we use for that. And again, like I said, we'll get into more specific examples later. But just understand, that's why we don't have two different constants here for the capital F of x and the capital G of x. We only need one of them there. All right, so let's do some examples here. So I have a couple of them in here where we need to go back to our trig identities. So hopefully you recognize these. I'm just going to run through them, and if you don't know where they're coming from or whatever, just let me know. But these are all trig identities that you learned in pre-calc. Sine over cosine is tangent, so therefore sine squared over cosine squared is tangent squared. So I can rewrite this as the integral of tangent squared x dx. And then you might be looking back at your list that I gave you on the 651 notes and saying, well, there isn't a tangent squared. And you're right, there isn't. But we also know something else from pre-calc, that tangent squared is the same thing, is the same thing as 1 plus secant squared x dx. Again, it's important to have the dx there. And now this is something we can do because the integral of 1 is just x plus the integral of secant squared is tangent x. And again, there are two separate functions there, x and secant squared x or tangent x, but we don't need two separate c's to represent a constant. We just put 1 plus c at the end. Next one, a little bit of algebra. This is very similar to the one that we did yesterday, so let's just run through this. Again, whenever we have one thing on the denominator, we can divide that by each term on the numerator. So t squared, do t squared divided by t over, t squared divided by t to the fourth, you get 1 over t squared, which you could write that as t to the negative second if you prefer. That was a terrible parenthesis. Let me start over. Should have wrote it after I did my integral. Parenthesis, here we go, 1 over t squared. And then plus negative 2, let me switch up the color here, negative 2 t to the fourth divided by t to the fourth just gives us a negative 2. So I'm going to change this and write negative 2. Parenthesis dt. Now take the integral of both of those separately. So what do I get? 1 over t squared, the integral of that. And again, that's where it may help you to rewrite that as t to the negative 2. Add 1 to negative 2, and then divide by that number. So t to the negative first divided by negative 1 minus the integral of 2 would be 2t. Throw a plus c at the end. And again, more than likely you will see the answer written as negative 1 over t plus, not plus, minus 2t plus c. And that is your final answer for that example. All right, so next problem here, go ahead and pause the video and try this one out on your own, and then check back and see how you did with it. So, all right, so first thing we need to do is use some identities from trig, from pre-calc. So we have sine over cosine squared. That's not something we can take an integral of, so what we're going to do is we're going to split this up into sine over cosine times 1 over cosine. Okay, now you might be thinking, well, isn't cosine squared the same thing as 1 minus sine squared? And it is, but again, we're trying to think of integrals that we know. So the more familiar you are with the list of integrals that I had given you, that's going to help guide your simplifying process, because then you'll know what you're trying to get to. 1 minus sine squared isn't really going to help us out at all here in the denominator. So splitting this up into sine over cosine and 1 over cosine, because then from here we can say sine over cosine is tangent, 1 over cosine is secant. So I have tangent theta, secant theta, d theta. And if you know that list, if you have it memorized by now, then you already know that the answer is secant theta, and again we need to have that plus c there. All right, now let's do a couple of word problems here. Find the general solution of f prime, capital F prime of x equals 1 over x squared. That's one part, and then find the particular solution. So the first thing that we need to do is we need to find f of x. Well, if I have the derivative of f of x, then I have to take the integral of both sides. So that is going to be the integral of 1 over x squared dx. And again, you can rewrite this as x to the negative 2 if that helps you. That might help some of you to do the integrals of these, but it's not necessary. Especially the more times you do them, you will just get better at them. So, but this is going to be x to the negative first over negative 1 plus c, which I will then further simplify into 1 over x, negative 1 over x plus c. So that is your general solution. That's the first part there, where it asks for the general solution. The particular solution, what this means is we want to get an exact number for c, and in order for us to do that, we need a little bit more information. And we're actually given that information up here. We're given that f of 1 is equal to 0. That means that we have this point 1, 0 that lies on this line right here on that curve. Okay, so let's go ahead and plug in our values for x and y and see what we get. So y is 0 equals negative 1 over x is 1 plus c. So simplify this and we get that c is equal to 1. So what that means is that our particular solution is capital F of x is equal to negative 1 over x plus 1. And that is the second part there where it asks for the particular solution. Okay? Next example, we're going to look at a velocity particle motion, not particle motion, I'm sorry, like a projectile motion, that's what I'm looking for. So a ball is thrown upward with initial velocity of 64 feet per second. Initially, we use that S of t formula, but now we only need to know the velocity formula, which the velocity formula says negative gt plus v sub 0. So the velocity in this function here, we're going to have negative, gravity is 32 feet per second times t, plus the initial velocity, which we know from the problem was 64. So to find the position function, we're going to take the integral of both sides. So the integral of negative 32t is negative 32t squared. Add 1 to the exponent and then divide by that number, plus 64t plus our constant c. Now, the constant here is, specifically for this problem here, is your initial height, which we know here is 80. So S of t is equal to negative 32 divided by 2 is 16, t squared plus 64t plus the initial height, which was 80 for this problem. So that's the initial part. The first question, when does the ball hit the ground? Well, we need to set this equal to 0. Before I set this equal to 0, I'm going to divide out the GCF, which in this case is a negative 16. So negative 16, and then we're left with t squared minus 4t minus 5. And we can take negative 16, divide that over, and that's pretty much gone. So all we need to do here is factor that t minus 5 and t plus 1. Now, one thing that I noticed on that last test was some of you, when you had the square root of 4, you wrote plus or minus 2. And what you got to keep in mind is that we're dealing with time. So anything that's going to give us a negative number for time, we can ignore, because there's no such thing as negative time. So our answer here, the ball, or whatever it is, hits the ground after 5 seconds. Okay, so that's the second part. When does the ball hit the ground? Yep, so there's your second part. Last example here. Go ahead and pause the video and write that down. All right, so we have, I'm not going to read all of this. They sell this after 8 years of growth, the trees, the shrubs, whatever. Here is the formula for the rate at which the shrubs are growing. Okay, dHdt is a rate. So this is the rate that this will grow. T is measured in years, so 1.5 times the number of years plus 5 will tell us how much this tree has grown. So what we need to do is we need to find the height. So if we're trying to go from the rate of the height back to just the height in terms of t, we're going to take the integral of this. So that means we have 1.5 t squared. We're going to divide that by the new exponent, which is 2, plus 5t plus some constant. Okay, so all we're doing here is we're just taking the integral of both sides of this dt. Okay, so now let me clean this up a little bit. Oops, that was supposed to be an eraser. There we go. So we end up with h of t equals, I'm going to make that as 0.75 t squared plus 5t, and then to get the constant here, this says the seedlings are 12 centimeters when they are planted. That means we had the point 0, because time is 0 right when they're planted, and 12, which means they are 12 centimeters tall. So what that means, if I plug 0 in for all of these t's, what do I get? And that is 12. So that's where that number there comes from. So there's the height after t years. That's the first one. We just did that. The second one says, how tall are the shrubs when they are sold? Well, we know they're sold after 8 years. That was given to us in the original problem. So we're going to plug 8 in for t. So h of 8, not t, h of 8 equals, plug that in your calculator and you will get 100. Don't forget the units, 100 centimeters. So there's your second part, and that is the first part. And again, here's some problems for you to try. If you have any questions, let me know.